This is the unofficial math lecture for Algebra 51 BYU Homeschool, lesson 3.1, a function and graph of time. So we're going to learn about graphs and functions and how they fit together. Remember, a function or an equation, same thing, like y equals 2x plus 1 is an equation, and a graph is just showing that equation mapped out. So a graph is basically many points connected together. And usually when we do a graph with a line, we're going to connect all the points of this line together. So there's infinite number of points on the line. Sort of like how there's a lot of pixels on a computer screen. All those little dots come together and make up a whole picture. So there's lots of like tiny dots here on the line that make up a picture. We take all the points that are coordinates or answers to our equation. So for example, when x equals 1, y equals 3, the point would be 1, 3. And that's right here. 1 for x, and up 1, 2, 3 for y. So y, 1, 3 is the coordinate. 1, 3. So here is an example of an equation, and they want you to graph it out. And they're going to show you that you just plug and chug numbers for x to find little dots on the line, and that's how you get your line equation for the graph. So the first number they plug in is when x is negative 2, y is negative 3. So when you plug in negative 2 up here, we'll get 3 as the answer. And I showed that here. Y equals 2 times negative 2, which is the x, plus 1. When we solve that out, 2 times negative 2 is negative 4, and we add 1 to it, so it's negative 3. So then you come over here and you go over 2 to the left and down 3 because they're both negative. And there's your point, negative 2, negative 3. You can see when we plug in 1 for x, we get out 3, and here's that point on the graph. And they do that for all the points in this table. So those are just whole numbers, but you could also, as it shows in the next page, do half numbers, like 1/2. So when you plug in 1/2 to that equation, you get y equaling 2. Okay? So you can plug in an infinite number of equations on this line and get more and more dots. And then eventually, as you connect all the dots together, you'll get a line equation. For this one, you can see the arrow, so it means there's infinite number of solutions and infinite number of answers. We can plug in anything for x in that past equation. We can plug in any number for x and get any number y. So that's why the line for that problem looks like this. So a graph just tells us, like once we graph something, it just tells us important information quickly. We can see how fast something's changing, if the change is positive or negative, as x gets bigger. So, the phrase picture's worth 1,000 words. Well, there's also the phrase a graph is worth 1,000 solutions or more. Because we can choose any point on that graph. When x equals this, we can figure out what y equals. Okay? Here's an example. First of all, it says a graph of a function is really a picture of a pattern, like we talked about. Patterns tend to relate something occurring over time, such as temperature of each hour of each day. You think about the temperature in the morning, it's really cold, and then it gets warmer and warmer as the hour gets later and later. So, if we measure the temperature of each hour, which would be our input data, or x, and we have our output data, y, the temperature. So when it's 6 a.m., it's 35 degrees. When it's 7 a.m., it's 37 degrees. And so if we plot those points, when x, or the input, is 36, the output's 35. So we plot all these points and we can make a graph out of it. Whenever you're making a graph, you want to make sure that like wherever your first point is that you're graphing, that you kind of leave some room in between so your graph can keep going both directions. So our first point was 6 a.m., but we're going to go back here to 5 or 4 or whatever, just to make sure we can graph it. So there's 6 a.m., 35 degrees, 7 a.m., 37 degrees. And then we connect the points on that line, and then we can tell when y equals 10, it's going to be 42 degrees. So at 10 o'clock, it should be 42 degrees. So it tells us something really fast. We know it's getting warmer and warmer pretty fast by just looking at a graph. Another example here is distance traveled over a 1 hour period of driving. Okay? So you look at a car, if you've been in the car for 10 minutes, you've gone 5 miles. If you've been in the car for 20 minutes, you've gone 10 miles. If you've been in the car for 30 minutes, you've gone 15 miles. So again, those are coordinates. 10 minutes, 5 miles is here. So 10, 5, 20, 10. Okay? And now they're talking about rate or speed. You can tell your rate or speed by taking the output and dividing it by the input, or miles per minute in this case. Okay? So rate equals output divided by input. Example here is miles per minute. If we take 5 and divide it by 10, then we get 0.5 miles per minute. Note that the units stay where they are, even when we make this fraction into a decimal. Okay? So you keep miles on top, minutes on the bottom. Miles per minute. Example 3 is talking about making your own graph with some input and output data. It's saying time your breaths for 10 seconds, 20 seconds, and 30 seconds, okay? And record how many breaths each time. So I did mine, and I breathed once in 10 seconds, I breathed twice in 20 seconds, and I breathed 3 times in 30 seconds. So if we're looking for rate of breaths, I can take any one of the outputs and divide it by the input, like 2 divided by 20. But I did 1 divided by 10, so 1 breath per 10 seconds. And here it is here. 1 breath per 10 seconds. Okay? And that would be 0.1 breaths per second. Okay? And then down here, they're going to teach you about changing units from one to another. For example, changing feet into miles. So you've done this a little bit before. Whenever you do this, it's called unit analysis. If they ask you for a definition, unit analysis is changing one unit to another. So here they want to know, they want to convert 7,000 feet into miles. How many miles is 7,000 feet? Okay, so we start out with 7,000 feet, and we know that there's 5,280 feet in every mile. So now, since 5,280 feet is the same thing as 1 mile, we can times 7,000 feet by 1 mile over 5,280 feet. Because it's kind of like timesing by 1. 1 mile is the same thing as this many feet. So it's not changing how long this is. It's still 7,000 feet, but we're changing the units to miles. So we're timesing it by pretty much 1 here. It's the same thing on the top and the bottom, just written with different units. So 7,000 feet times 1 mile divided by 5,280 feet. Notice that the feet here and the feet here will cancel. If you remember, if we have multiplication problems, this is an example of why things cancel. 3/5 times 1/3. The top cancels with the bottom, and then we end up with 1/5. So when you have feet, because this is basically like 7,000 feet over 1, you have feet on the top and you have feet on the bottom. The feet cancel out, the numbers stay here, and then you times the top number by the top number and the bottom number by the bottom number. So it's 7,000 miles divided by 5,280. And the feet cancel each other out, the miles stays. So it's 7,000 miles divided by 5,280. And if we look that on a calculator, 7,000 divided by 5,280 is 1.33. We'll keep the miles. Okay, and they're saying if you round to the nearest hundredth, of course. All right, we're going to do another unit analysis, changing 15 minutes into hours. So I know that there is 1 hour in every 60 minutes. Okay? You could rewrite this as 60 minutes in every 1 hour. You can times it by whichever one of these makes sense to get the unit you want on the top, because the unit on the bottom that you're timesing by will likely cancel out. We want hours, and so therefore we're going to put hours on the top, because there's 1 hour for 60 minutes. So we're going to use this one, and we're going to times it by our 15 minutes. 15 minutes times 1 hour per 60 minutes, right? The minutes cancel. This is like 15 minutes over 1. So 15 times 1 is 15. 1 times 60 is 60. Minutes have canceled. Keep the hour. So we can write this as 15 hours over 60. Or we can divide 15 by 60, which is 0.25. So this is equal to 0.25 hours. Example 5 is another unit analysis, changing 15 inches into, this one's like kind of crazy. It's 2 rates. So if a snail was going 15 inches per minute, or a turtle is going 15 inches per minute, we want to know feet per hour.
Ladies and gentlemen, this message is coming from...
So we start out with 15 inches per minute. So 15 inches for every 1 minute, or 15 inches divided by 1 minute. 15 inches per minute. Then we're going to times by our conversion factors to get what we want on top. We want feet on the top, and we want hour on the bottom. Okay? So for every 1 foot, there's 12 inches. So we times this first number by 1 foot over 12 inches. Notice the inches will cancel. And we're left with feet over minute here. We want feet per hour. So we want to put hour on the bottom. Okay? So we times it by 60 minutes per 1 hour, because there's 60 minutes in an hour. Then the tops and the bottoms cancel for minutes. And now we're left with feet per hour. Okay? And then we just do the math across the top and the bottom. 15 times 1 times 60, or 15 times 60, which is 75. 1 times 12 times 1 is 12. 15 times 60 divided by 12 is 75 feet per hour. So 15 inches per minute is the same thing as 75 feet per hour. Same thing, just different units. Okay? So this will probably be a little bit confusing at first, but once you get the hang of it, it will roll. So after you get done with this video, do all the math labs, and then watch the videos for those and start your quiz. Good luck today, buddy. Love ya.